types of elements. Like a lot of this might be foreign language to you guys, so again, ask questions if you want, but I understand you might come back and look at, I did this so you could reference it later once you've taken more classes maybe and tried it a couple times. This might make more sense to you guys. But okay, so 1D elements, right? So basically 1D, 2D, and 3D are the types of elements, right? So 1D elements, if you have 1D elements, you can only apply forces and constraints at nodes, right? So you have to be, when you make those, if you have an I-beam and you want to put a load in the middle, you have to break that into 2 sections because you need a node in the middle to put a load on. Where if it's a solid mesh, you could put loads anywhere, right? So, so just know that when you do 1D elements, you got to make sure you have nodes where you need them. So a spring can be a 1 degree of freedom element, or is a 1D element that has 1 degree of freedom, right? So you can put springs in your model, and you just type in a stiffness. Doesn't matter what the geometry looks like. You just put in pounds per inch, whatever. So springs are 1D elements. So this is where it can get kind of complicated. There's a rod, or you also see it called a truss. And some softwares have a little bit different meaning between rods and truss. But if you do a rod or a truss, it can only support axial loads. Okay, it doesn't take bending or torsion or shear. So it has to be truly a truss structure, right? It has to be built to where you only have nodes or forces at nodes and reactions at nodes, and it's all transferred through compression or tension. Okay, otherwise you're gonna get errors. So, but it's super quick to run analysis that way, and it's super simple. So you have a rod and truss. Some softwares actually, this is where you have to check your software, will allow rods to take torsion too. So just make sure when you start a program that you understand the definitions of their elements. Okay, a bar will support axial, bending, torsion, and shear, but it has to be symmetric, right? So you can't have like a C channel or an L channel where the neutral axis is not also the shear center, and so bar and beam are the same exact thing if it's a square or some kind of symmetric thing. A bar or a beam element will give you the same results. But if you're using something that's not symmetric, then it's a beam. And so a beam supports all types of loading, right? So bending, torsion, shear, and it can be non-symmetric. I highlighted in green because this is the element that I think is the best element to use, is 1D beams. That's the quickest solution, the most robust. It's hard to screw that up. Like out of the rest of these, that's the most robust one to start off on. However, it has to apply to your load case, right? I mean, you can't always do that when you have a solid geometry that has loads in different places. That it's just not a beam, right? And I'll get into a little more details on some of these elements later. Okay, so then you have 2D elements, which can be a little bit more confusing and more complicated. So you have a plane stress element. So these only support in-plane loads, like a membrane, right? Cannot support any out-of-plane loads at all. So it's very specific when you want to use those. But then you have plates, which supports out-of-plane loads only. So it can bend in two directions in the plane. You model this as a plane with just a user-defined thickness. So you can either take the CAD geometry and tell it apply the CAD geometry, or you can just type in it's a plate that's this thick. Okay, and then shells are kind of the combination of the two. So a shell supports membrane and bending loads, and it can be curved, which is useful. So like if you had an I-beam that was curved, you couldn't make that a beam element, right? Unless you made a bunch of small ones, right, and a bunch of straight ones. So if you have a curved one, you can just make it. You can make it a plate or a shell. Excuse me. You can make it a shell, and we're going to do this in an example. And that's kind of like the best use of it is when you have like things that you want to be beams, but it has a weird shape to it. That's when you use shells. So you want something with a high aspect ratio, something on thin material like 10:1. So you can use shells on like a Baja frame. You could do shell mesh. I recommend beam, but you could also use shell mesh, not solid mesh, and that's what we'll get into that. So things with high aspect ratios like this, you don't want to do solid meshes. You want shells or beams. Yeah, I think I hit all those other points. Oh, so on this side, so when you do a 1D, this is what you have to do in the software. You when you draw it, you have to give it a length. So you just have to give it. You have to define its geometry by just the length. That's all you're telling it, and then you have to give it additional input, which is what's the area, cross-sectional area for that length. The way you do that might be modeling it, or it might be typing it into the FEA program. When you do 2D elements, you have to actually define the area. So you define the area, and then you just have to tell it what the thickness is. Okay. Now we're going to get into 3D, which you guys probably have been mostly using 3D, I'm guessing, if you've been doing FEA. In this case, you're defining the whole volume through your CAD, and there's no other user input you have to give to the FEA. It has everything as far as the geometry. So 3D elements, tetrahedral, can be used on any 3D geometry. This is, like I said, this is the ones you're probably going to see in SolidWorks. There's a bunch of different types. I didn't even put them on here because I don't want to confuse you guys, and I don't know mathematically the difference between all of them because I don't come across a lot of these other ones. But the tetrahedral will give you is probably the one to stick to, and I don't think in SolidWorks you can change it, but and other ones they'll give you like 8 different options for what the shape. This is what the tetrahedral looks like. What kind of shape you're going to use for 3D meshing, and it depends on how it's going to and how many nodes you're going to have and how it's going to do geometry. These other ones I put on just so you know, but we don't really use them that often in my experience, which is bricks or prisms. So these have very high aspect ratios, which reduces your mesh size, basically reduces your degrees of freedom. And you use this when you either don't care about a section of the part, or it's just not an area that's highly loaded or something like that. And so it's basically a large element that's relatively stiff. And an example would be like in a rim, maybe, and you're trying to look for elements like on the spine or on the spokes, and you don't care about the surface where the tire mounts. Those could all be bricks, basically, and then you mesh the spokes a little bit. I can't read the bottom of it. Oh, and then the bottom says pyramid. And a pyramid is what you do when you transition from bricks to tetrahedrals. So on the rim, if you have bricks on the outside, you can't transition right to a tetrahedral. So you have a pyramid, which does that. Okay, here's some examples, and this is the case study that I'm going to do after this presentation. We're going to take an I-beam and we're going to model it using 1D, 2D, and 3D mesh and see what you think the best results are. So if you do 1D, this is what your CAD model would look like. So again, it's not I-beam. I drew a line. This is the simplest you can do to model anything. You just have a line, and then you're going to make elements off of that line. So in the CAD model would be a line. I use what the weldment feature in SolidWorks. So that's what it looks like when you apply the weldment. I didn't have to draw this at all. And then this is what the mesh looks like. So you have to start, in your mind, separate CAD from the mesh or from elements, because visually they can look like anything. It doesn't matter because it's the math that matters. So this looks like a hexagon or something, right? And it has a bunch of elements. Even though it's 2 elements, it broke this mesh up into a bunch of different elements. You might think that's the geometry. That's just how SolidWorks represents it, because there's no point in using memory to draw that, because it's just a number, right? And so, in fact, you don't even need anything. You can just be aligned with the number. So don't get scared when you see meshes that don't look like your geometry when you do 1D, because it's just a representation. It's not trying to represent the actual hardware. Okay, if you would do this in 2D, you'd actually have to draw this CAD model out. I guess you could still use a weldment feature, but you would draw this. So this is actually, there's no line here. This is a sketch that's extruded. You would have to make mid surfaces, right? So when you do a 2D, you just have a plane, right? It's infinitely thin. So you have to make mid-surfaces out of this I-beam, which there's a feature to do that in SolidWorks. When you do that, you're going to have a little gap, right? It's going to do a mid-surface here, it's going to do a mid-surface here, and it's, there's going to be a gap between where this mid-surface ends and this horizontal one begins. So then you have to do more work to extend that surface and join them, right? Then this is what the mesh would look like. So the mesh looks just like the 2D here's all the elements broken up on it. Now you can turn on the thickness of the elements to see what the geometry looks like. And this will represent the geometry better than this one will, but it's not exactly perfect because you're going to have it's going to look like you have interference. The math's going to be right, but when you extrude this and extrude this, it looks like you have like double material on top of each other, right? So you're going to see weird things when you do 2D meshes, but the math is what matters. Okay, and then the 3D mesh, you model it the same as you would do here, and you can skip that and you just mesh it. But you can see out of all of these, this has the denser mesh, right? This has a lot more elements, and it's a lot more labor intensive, at least for the computer, which will matter as you get bigger and bigger models and you want to iterate a bunch of times. Any questions so far on like the meshes? I know that bars versus beams versus plates can be confusing, so you might have to read that a couple times. But it's important to know if you do the wrong element, you can't take certain loads and your results are going to be wrong. So it's important to understand those.
Kevin, which ones would you suggest if they're doing like the frame versus like an upright versus, is there some common suggestion for
I have a slide on picking elements, but I can still answer that. I mean, for frame, 100% it's beam elements. It's 1D elements for frame. Right. You should not be meshing a frame that has hollow tubing, right? Even if it was solid rod, you would still use beams. So any kind of truss structure or anything like that, you want to use beam, even if it's not a true truss, because like the frame's not a true truss, right? You need to have with the frame, if you're going to have like loads where the suspension comes in, you need to make sure there's nodes at the suspension points. But yeah, 100% you should be doing beam elements for that. And you can combine, and I'll talk a little bit about that. You can combine, like you can have a thing that has beams that then transitions to 3D solid and stuff like that. Solid mesh, I think later I go into choosing the elements. But was there, any other questions that anyone's hung up on? Because I'm going to reference these going forward. This one might be, I don't know if how SolidWorks does these. I didn't try to do this in SolidWorks yet, but there's other types of elements called rigid body elements, so RBEs. So these are rigid connections between mesh components. So they typically see them as like, they call it a spider connection when you want to like connect a central node, which is the independent node, to a bunch of other nodes which are dependent on that node. And so for example, if you want to do a bolt, this would like kind of represent the washer. And so you would have a central node and a bunch of other nodes connecting this. And then you could like put a load on that center node and it'd be like loading your part. That's not the best way to do fasteners, that's just an example. That might be the best way to do it in SolidWorks, I don't know. So there's a difference between RBE2 and RBE3. I don't know what happened to RBE1, but there's not an RBE1. So RBE2 will add stiffness to the model. All the nodes will displace the same amount. So you have a center node here, and if it displaces 0.5 millimeter, all the nodes attached to it have to move up with it at 0.5 millimeter. So you artificially rigidize that whole area that's connected to that. Another way to think of this, another example might be if you had for some reason you were trying to tie a plate with like some bolt holes together. Let's say you had a load. Let's say you're pulling up on this plate, and so you made an RBE2 like here, and you're going to pull up on it, and you connect it with spider nodes to these other things. You want to see what the load in the plate is, or at these forces are, or at these holes are, if you're pulling up on this plate. If these are RBE2s, when you pull up on this, it's basically making this whole square rigid. It's going to bypass the structure. This could be paper, it doesn't matter. It's going to treat it like it's a brick, because however much this node moves, these other ones have to move the same amount with it. Okay, so you're actually going to get the same forces in all 4 of these holes, basic, right? Because you're going to have the same displacement. So if you do an RBE3, the center node is distributed to the other nodes, right? So, if you put, 100 pounds here, if it's a RBE2, you're going to see 25, 25, 25, 25, even though you should see more loads where you're pulling on down here. So RBE3, if you put 100 pounds on, you might see like 30, 30, 20, 20 or something like that. So it matters when you're using RBE2 versus RBE3. The one way I remember that is I use the 2. The RBE2 is too stiff. That's how I remember that, right? RBE2 is too stiff. That's how I remember that. So I usually am using RBE3, but there's times to use RBE2. Like doing this with RBE2 is okay because you have a washer there. You're not trying to determine the deflections of the washer or anything. You're assuming basically the washer is rigid relative to this material, right? So it's okay to do that, and it might be more appropriate to do that. So I don't know if I haven't tried to put RBEs into SolidWorks simulations, so I don't know what they call those if they have rigid elements there. So like an example would be like the engine. Let's say for Baja you wanted to see the loads on like the engine plate or something like that. You're not going to model the engine. There's no reason, right? You're going to have a mass, right? And then you got to put that mass, almost like what I just drew, to 4 points. You don't want those to be RBE2s, or your whole plate's going to seem really stiff. Okay, and then there's non-structural mass, which is like what I just talked about. You could put non-structural mass to represent an engine or something that you're supporting that's not adding stiffness to your model, right? So non-structural mass is very useful, and instead of having to put loads like a force in a certain direction, you can just put a non-structural mass, and you have to turn gravity on if you're doing stresses, or you can, if you're doing modal analysis, it doesn't matter. You just have a mass there that's part of the spring mass system, right? Yeah, this was another example. I think you guys get it. Okay, here we go. Choosing an element type. Okay, so you first think, what's the analysis used for? Things like, is it a quick study? Is it a long-term model? It might be a sensitivity study where you're just trying to see the difference between 2 different things. You don't care necessarily about the absolute result, and so you just want like the quickest, result. Might change the type of element you're using. If it's a long-term model, like maybe eventually it's going to turn into something that needs to be a solid mesh. They might change how you approach it. But more important than that is like, what loads and what boundary conditions are you applying, right? Do you have out-of-plane loads, right? Because we talked about elements that can't support out-of-plane loads. Do you have to constrain the model over an area, or can you pick a node? Can you pick a point? Where are you constraining this? Because that'll determine where you have elements, where you have nodes, and you might actually have to add surfaces. Like on a solid mesh, you might have to add a surface to apply a load to, because it doesn't really exist in your model. Yeah, that's how our load is being applied. So like I said before, you want to stick with beams and plates whenever possible. I said plates is really shell meshes is probably what you can use more often. However, for short structural members, where you have a ratio, and I think I have a chart on this later, the ratio of its, the longest cross-sectional dimension over its length is less than 3. It's going to tell you it doesn't want SolidWorks, at least. This number applies to SolidWorks. I don't know what other FEAs probably don't warn you at all. They just think you know what you're doing. If it's less than 3, it's going to say you need to use a solid mesh. The reason for that is, as you know, if you have a short, stubby beam, when you do beam formulas, bending, dominates most of the time, and transverse shear is not, a big driver in your overall stress. So when you get a short, stubby beam, like if you're calling something a beam, but it's only this long and only like this wide, it's like super deep but really short, transverse shear is actually going to dominate more than bending. I think I've heard 4-to-1 before, but SolidWorks assumes, I guess, 3-to-1 is no longer really treating it like a beam, and so it wants you to do solid mesh. So just know that you'll get a warning. If you know what you're doing, you can ignore that warning. If you know that you're not worried about transverse stresses, or it's not loaded, maybe it's just all axial load and it doesn't matter. So there's times when you don't want to use beams because it's not appropriate. So solid mesh, which I think most students start with solid mesh, I understand why, because you're just like, it's solid geometry, let me just do the solid mesh and not have to worry about what kind of loads there are, plates or beams. However, you should try to avoid solid mesh. Some of the problems are you'll get, relatively speaking, extremely long computational times, not just to mesh it. You'll see your little bar going every time you mesh something, and then it's going to run a little bit longer. I mean, that stuff adds up, and especially in industry when you have millions of degrees of freedom in models. We have models that take over 48 hours of just the computer running to solve. And so when people want to iterate on that, you're telling me I have to spend a week to do one iteration, basically. That's expensive. It's also a difficult and long iteration process, because to redo something, you have to basically change the geometry and then remesh it. So like in that I-beam example, let's say I go, oh, this is I-beam not strong enough, I need to make it thicker. I have to go back to my CAD, make it thicker, remesh it, rerun it. Whereas if I have a beam, I just go, oh, let me make the inertia of this, and I just type in a new inertia. Or you can, if you have a plate, you just go, oh, make it a 1/4 inch thick instead, and rerun it. You don't have to go back to your CAD model and change geometry. So it's a long process to redo that. And then sometimes, actually maybe every time you do that, you might have to redefine your loads because you have a new mesh now, and the node that you're applying something to now doesn't exist there anymore. So, and then you're going to get a very dense mesh for some areas. So you have really small features, you're just going to get a million elements in that area, and it's probably not going to give you accurate results, as we'll talk about later, about why element shapes matter. Or you're not going to get enough elements like through the thickness. So if you have like a 35 thou tubing, an 035 wall tubing, that's pretty long, it's going to just give you one element like through that whole thickness, and that can give you inaccurate results when you have bending, right? And remember I said elements average out stresses, right? So if you just had one element through the thickness, and the top's in tension and the bottom's in compression, right? Because you're bending, and let's say this was like the center of it, and this is the element node. You might have like minus 1,000 psi on this, or plus 1,000 on the top, and plus 1,000 on this side, and this might say minus 1,000, right? Because if the neutral axis is down the middle. So if you look at average elemental stress, it's going to tell you there's no stress in this part. It's going to say 0, right? So you need to break this up into 2 elements. So now this says 0 here and 0 here, and minus 1,000 here, minus 1,000 here, right? So you want at least 2 elements through the thickness. And some people will tell you need 3 elements through the thickness. And sometimes it doesn't matter, because if depends on your load case. If you might get a perfectly good result if it's all axial load. But that's a problem, is you have to go check all your thin walled areas and make sure you have at least a couple elements through the thickness, which can be complicated on a complicated part. And then you also need to check for element shapes to see if there's any bad ones, and I'll talk about that in a second. Okay, so often you will start with a larger assembly using beams. So for example, for Baja, maybe you want to analyze your A-arms or something like that. You could start with beams everywhere, and let's say you have loads on the frame that are transferring your A-arms or something like that. You can then get the input loads into your suspension using really simplified beam geometry everywhere, and then zoom in on your A-arm and do a solid mesh of your A-arm or something like that, right? So in fact, SolidWorks has something called submodeling, which I didn't really get into too much, you can do a sub-modeling study where you run an analysis with multiple components, and then you do a sub-modeling. So let's say it's a kingpin. You have the kingpin and the A arms, and you have the load on the kingpin. That's where you know the load's coming in. You could run an analysis of that whole thing together, where you have loads just on the kingpin, and then tell it to do a sub-modeling, taking the loads from the kingpin and how they transfer to your A arm, and just model the A arm using the input from the previous analysis, basically. So that's what sub-modeling is. And you can also switch element type in SolidWorks. Even if you started off trying to do solid and realized, I don't want to do solid anymore, I actually found a feature that you can treat it as a beam. So you can actually change to shells and beams and stuff, even with solid geometry. However, like I said before, if you didn't go in knowing that, you're going to have one long element, basically, that you can't put loads in the middle of it, so you have to split that into several bodies. So just some things to think about when you check elements. And then here's the rule of thumb. Sorry, this is kind of the inverse of what I was saying before, the 3-to-1, right? The 3-to-1 number is like right here. So this is, again, the ratio, the thickness and the length ratio. This is kind of just a rule of guide where if it's thick, that means it's a good region to use that kind of element. And then this is not as useful, you're probably getting bad results, and then like never use it beyond this. This is kind of what it's telling you, right? So these are the thin shells and beam elements. And so this is like 3-to-1. This is a 2-to-1 ratio. So you can use thick shell and beams. You can see the beam elements kind of apply in a lot of places. The 3D elements here, you only want to use when you're getting down to these kind of ratios, right? So this is saying like if you have a half-inch thick tube, if it's any longer than an inch long, it shouldn't be a solid mesh, right? So you can take the inverse of these numbers. It might make it easier in your head to think of ratios. I almost put that in this chart, but
for tubing, would you do like OD or thickness for the height here?
No, for
or am I thinking of this wrong?
No, I would use the
Tube
wall
thickness.
thickness. Yeah.